Hi everybody, I'm Federico Di Giacomo from the Italian National Institute for Astrophysics, and this talk is on behalf of Claudia Mignone, Rachele Tognolo and Stefania Varano, who are working with me in order to analyze and evaluate some educational workshop. So, 2 years ago, more or less, we realized a virtual exhibition entitled Look Up. Look Up is a virtual exhibition accessible from any device, PC, smartphone, tablet, Oculus, whose the primary goal are to enhance, describe and give maximum diffusion of the entire collection of stellar atlas, cometography and selenography preserved in the observatory of INAF. The collection of the celestial atlas play an important role in the history of modern culture and represent a real milestone in the scientific revolution. Using the content covered with the exhibition, we have realized 6 educational workshops. 2 workshops are regarding the stars and the constellation, 2 are dedicated to the moon and the lunar phases, and finally 2 are developed to the planet and especially about describe Mars. The main goal of these activities is to raise awareness of scientific development, even in area of great social fragility and early school living. In that, these activities have been developed in a partnership with Save the Children Italia and were carried out in its light point. The light point are places developed to guarantee a future for children living in a most disadvantaged area of cities through free education and support to the educational community. This activity began in November 2023 and involve 7 light points spread across the entire national territory: Turin, Milan, Venice, Rome, Naples, and Palermo and Catania. And more than 300 children with an age between 6 and 15 years old took part in the various activities. So, to evaluate both the degree of satisfaction and the learning of the various workshops proposed, all participants were given a simple test, a simple survey before and after the activity, with a few questions regarding the topic covered. And in this presentation, we discuss the evaluation of the workshop conducted with the youngest children group, corresponding to the age about 6 and 10 years old. To assess both the effectiveness of the activities and the satisfaction level of the children, a brief survey was administered to all participants before and after the activities, with a series of questions related to the topic covered in the workshop. The analysis of the collected data helped understanding the participant knowledge level and allow for improvements to be made to the activities, enhancing their engagement and efficiency. Participation in the survey was fully anonymous and optional. Children could choose to answer a few questions, all of them or none, as they prefer. Overall, all the children found the activities interesting and fun. But we found a very big problem in our survey, because the initial evaluation questionnaires were heavily text-based, with multiple choice answers. In some areas, children could read and answer questions easily, but in other areas, children's literacy was very low, making this evaluation unfitting to the context. During the first workshop, the facilitators realized that they needed to read the question and the multiple choice answer to the children. breaking them down to their basic concept, but basically influencing the answer with a high risk to introduce bias and false positive. To bypass this bias, we ask them to draw the answer to some question relevant to the workshop content. The graphic form is very powerful and is widely used in evaluation with a very young children and in case of language barriers. In this case, we demonstrate that graphical evaluation allows us to bypass communication issues due to low literacy as well as cultural barriers in context of social marginalization. A total of 70 pre- and 45 post-activity questionnaires were collected at the end of the various workshops. Pre- and post-questionnaires had similar questions forced in a different way to make the activity less repetitive. All pre-questionnaires include the questions "What does an astronomer do?" and all post-questionnaires include the question "Did you have fun?" Other questions varied depending on the content of the workshop: stars, moon, planets. Besides, the sample of children who responded to the pre-activity questionnaire doesn't coincide with the post-activity one. Therefore, a full pre-post analysis cannot be performed. So, we conduct a case study analysis comparing the response to identify overall trends. One of the workshops, Stars in Perspective, concern the distance of the star and the constellation. In this workshop in particular, the children realize a 3D model of a constellation, in particular of Cassiopeia constellation, using some different pieces of wood with the dimension of the real distance of the star from us. Thanks to this workshop, we can explain that, contrary to the common perception, the constellations are not made of stars close to each other, but the stars that are located at a different distance from the Earth. An interesting result from the evaluation of this activity is the comparison between the representation of stars drawn before and after the workshop. In the pre- and post-questionnaires of the workshop, we ask to the children to draw a star. All pre-activity drawings feature the classical 5-point stars aligned with the common misconception. So in one drawing, the classical 5-point star persisted. In the other drawing, a child reproduce what he or she perceived during the experience. The stars are sphere-shaped objects mounted on a stick. This change in representation is dense in a meaning and conveys additional information about the children's perception that cannot be accessible using a multiple choice or open-ended questions. Another interesting workshop is the moon phases in a box. So this workshop concerns the origin of the moon phases. So in this case, the children realize a box with some different windows on the different part of this box. They put a ball inside the box and then they light up this ball with a lamp. Then they observe how change the shape of the shadow of this ball, watching this ball, this moon, from the different window on the box. Only the pre-activity questionnaires include a drawing question, which contribute to valuable insight regarding the children's representation of the moon. In fact, children reported a multitude of representations that can be classified in two main categories. The main one is a single circle with a colored dot that represent craters and or maria, while the second and the piece a full circle without craters, together with a crescent moon. There is also a third one, which is a single crescent moon. The three types of drawing convey different conceptions about the moon. The first one, the sphere with the different crater, reveals the idea of the moon as a single sphere-shaped object with irregularities on its surface that are clearly visible. The second one unveils an idea of the moon strictly correlated with its phases, which make it appear in different shapes. The fact that some children choose to depict all of them in some drawing as opposite to the third representation may raise some doubts about their knowledge of the moon as a single object. Indeed, this kind of drawing can be interpreted as either distinct versions of the same object or different kinds of moon. This reflection made us decide to show more in detail during the activity that the moon is a single sphere-shaped object that can change its appearance due to its illumination. Finally, the long live resolution workshop dedicated to the image of the solar system, the planet dedicated to the image of the planet of the solar system, include a graphical question asking the children to draw a telescope or binoculars. Only pre-activity questions were collected, unfortunately, and this question include 7 drawings. All drawings tend to show a single tube-like instrument, and in 3 cases with a shape that represents more articulated, as if to indicate the presence of different elements, for example, eyepiece, lens, and so on. Direct experience carried out during astronomy hands-on workshop in communities at the outskirts of big Italian cities, marked by social marginalization, high rate of school dropout, low literacy, and the presence of non-native Italian speakers, have shown the power of drawing as a non-verbal form of evaluation. Through drawing, everyone can express their experience, emotion, and level of learning, offering a valid tool to understand the impact of the activities. This approach allows for an inclusive and intuitive evaluation capable of involving everyone regardless of their linguistic competence.
Hello. Today we will be talking to you about the challenges of teaching and evaluating astronomy activities in Croatia. My name is Daniela Takac. I'm a naik from Croatia and elementary school physics and technology teacher.
My name is Ana Maria Zaninovic. I work at a high school in Zagreb, like teacher. I teach physics and astronomy.
Okay, so astronomy in the Croatian curriculum. In the elementary curriculum, there is no astronomy as a subject. So astronomy doesn't have its own curriculum, but it's integrated in a lot of different subjects. And also, it can be taught as an extracurricular subject outside of the regular classes.
In high school, we can find astronomy topics in physics, chemistry, biology, and it can be part of school curriculum as an elective subject. If you have enough students, you have elective subject astronomy.
So we did a little small research study about the position of astronomy in Croatian schools. We had 50 high schools and 50% of elementary schools. Most of the teachers have more than 10 year of experience. Only 11% have less than 5 years. 50% of them have astronomy as an extracurricular subject, and only 27% of them have astronomy as an elective subjects where they grade students, and all of the others have them in a different kinds of way, like mentoring work, or just doing work for the competition, or doing it in their free time. What is interesting is that they have it one hour a week, 64% of them, and 35% of them teach 2 hours a week. And only 33% of teachers have it paid or in their regular salary, and all the others have it inside their work hours or outside of their hours in their free time. Students that go to astronomy, that attend astronomy classes, have a very, very big interest in all other areas of STEM, 72% of them, and a little smaller interest, 27% of them. And there is no student in astronomy that doesn't have interest in STEM. So most of them have interest in physics, 38% of them, and 16.7% of them in mathematics. All the other colors represent different subjects or cross-curricular subjects, all of the subjects of STEM areas. But what we found most interesting when we asked, what do students choose when they finish elementary school? 100% of students choose STEM high schools, but after they finish the STEM high school, 60% of the students that attend astronomy choose to go to computer engineering universities. Only 26% go to physics universities, and 13% go to maths. So it's kind of different than astronomy. But in Croatia, we don't have an astronomy in any university, not even a course inside physics. So how can we evaluate astronomy in middle school or elementary school? Only through different kind of project-based learning in 5th grade or in 6th grade, where they do a little more projects in astronomy, which also we use to prepare them for the national competition. So they can do project-based learnings in physics because they have physics only in 7th and 8th grade. So then we do a little more complex subjects like atmospheric extinction or building a magnetometer. Also, we do a lot of different project-based learnings like space materials, meteorology, Mars rover. So we did a big project about ExoMars. We simulated the ExoMars mission. Also, we do project-based approach in PE. So they can do like training like an astronaut or something similar. The biggest thing that we have seen through our research is that there is a big gap between middle school and high school knowledge in math skills, physical content for schools like scientific method or ICT knowledge of ICT programs. What we found that, of course, what Anna found, because she works in high school, is that students that had astronomy in elementary school came to high school with much better math skills. They knew the scientific method through all the things they have done in astronomy, and they helped to bridge this gap in knowledge that is always there because of the very different curriculum in elementary and high school, which is not which is the ministry problem. So
in high school, students independently research astronomical terms, present selective topics, solve problems in astrophysics, observe astronomical phenomena, visit to observatories, exhibitions, and workshops. Those are some examples of project topics in high school, and astronomy in high school is interdisciplinary learning. They work some themes like astrophysics, astrophotography, field teaching, spectroscopy, and photometry. They visit observatories, exhibition, and workshop, and so.
yeah, Anna and I do a lot of things to popularize for the popularization of astronomy in Croatia. So we organize a lot of webinars where we host teachers who do a lot of things, or well-known scientists. We do stargazing parties. We do a lot of things with the little ones because they are the future of astronomy and they should know the astronomy from a very young age. The problem is evaluating. So most of the teachers use astronomy national competition for evaluations of students, because at the astronomy competitions they have to have a test, but they also have to present a topic, a poster of the research they did. So as you can see, 100% of teachers prepare them for astronomy, and it's mostly 1 to 2 up to 4 hours. The school national competition has 3 levels: school competition, regional competition, and national competition. So the students have to go through all these 3 levels in order to present their research paper and get it graded. So they always they have a test, like knowledge test, and then we evaluate their research in this rubric. So we look at the overall research work, we look at the purpose of the research they made, description of methodology, presentation of the research results, discussion, sources they use, and how much effort did they invest. Usually there are 2 reviewers of each research. Students do it like a real scientific research. So these are some of the examples that they did for national competition in high school. They are really high level, and students have to defend them in front of the jury that is usually from 3 people, 2 scientists and 1 teacher, or 2 teachers and 1 scientist. Here you can see some other examples. And what we have concluded in our research is that everybody would love to teach astronomy, but there are many problems with it. Like the curriculum is very hard. Teachers are not evaluated enough. They are not paid enough, and you need a lot of organization, and you need a lot of support to teach astronomy, because it's a very hard subject to teach, especially if you want to go to national competitions. So we hope to change this very soon in our country by popularization of astronomy, and doing a lot of teacher trainings for the younger teachers. So this we hope that we fit this in 10 minutes. So thank you for your attention, and hello from Croatia.
Hello.
Hello, everyone. Today we are two people presenting this talk. I am an astronomer in Chile, and Javiera Núñez, who is a physics teacher and who presents this work as her final dissertation to obtain the physics teacher degree. As a motivation of this work is that Chile is one of the most important countries to develop astronomy research. However, the content of astronomy in the curriculum is scarce and fragmented, as was demonstrated by a recent study published by Rodriguez during this year. Since 2022, the CIRAS Center at USACH created a pedagogical team composed of astronomers, high school teachers, and science education specialists in order to conform to a professional learning community, which is centered into collaboratively co-create didactic sequence using real astronomical data to incorporate frontier astrophysics into the science subjects of the high school level. This team has created a lot of didactic sequences to teach in subjects such as mathematics, physics, chemistry, and also biology. All these activities have been implemented in the school of the teachers' teams to validate the disciplinary and pedagogical content of the proposal. This work has been preliminarily demonstrated by a change in the students' perceptions about the scientific work. However, this educative material is not ligated to a validated instrument to measure the impact of working with astronomy real data in the classroom. To test if the didactic sequence based on the real astronomical data works, we search in the literature. However, most of the instruments are related to measure level of knowledge related to fundamental astronomy at school level. Last year, the Shaw-IAU launched the Evaluation Framework and Toolkit, which contains a theoretical basis and tools to collect data to evaluate activities that use astronomy for the education, and also guidelines on ethical concepts for the collections of data from astronomy activities for education. Different types of tools appears in this manual. The use of each depends on the objective of the activities, the audience, the format, the time, and the resources available. Based on the suggestion in the manual, we decide to use the questionnaire in pre and post format to measure the impact of using real astronomical data in the classroom. We base the creation of our tool on the astronomy and student attitudes, or also called ASA questionnaire, created by Bartlett et al. 2018, which is suggested in this manual. This questionnaire is an instrument to measure students' attitudes toward astronomy and science, where it assesses 8 main categories: interest in astronomy, interest in science outside school, hands-on work in science, teacher actions in science, perception of science ability, future aspiration in science, benefit of science, and personal relevance of school science. Our test is a combination of questions from the ASSA test and our own test. And it is in the form of pre and post tests for comparison. The methodology is mixed with questions in the Likert scale format, open and closed, so that the data allows both qualitative and quantitative analysis. In designing the tool, we first incorporate the ethical protocols suggested in the manual for collecting data from students in the classroom. This states that participation in the survey is voluntary and that the information collected will be kept confidential and used only for research purposes in the field of astronomy for education.
The categories of questions are based on the ASSA instrument, and they are student characteristics, perceived abilities in science, perceived interest in astronomy, practical work in science, future aspiration, and feedback. Examples of the question are shown in the table, both for the pre and post. To validate the instrument, we apply validation by expert judgment, which measures variables as sufficiency, clarity, coherence, and relevance, based on the criteria established by Escobar Perez and Cuervo Martinez 2008. So far, we have contacted 4 experts from areas of work such as science education and physics teaching. Their academic profiles are shown in the table. So far, we have only managed to connect with science teachers, but none with a specialization in astronomy didactics, as this is still an emerging area in Chile. The judges' level of agreement was not high, mainly because they found the test contained very general questions. However, we believe that this test should be with general questions, as it is expected to be applied at the end of very varied activities and different science subjects at secondary level. In addition, we conduct preliminary validation by classroom implementation. Preliminary results of the implementation have shown that the activities generate a change regarding, for example, the student's perceptions of the relationship between physics data does indeed help them to better understand the subject matters of the physics class.
Well, finally, in conclusion, this work needs to go through further validation process before it can be considered as a tool to be applied to any activity using real data in the classroom. We hope to have a large number of judges who can review these tests, and since we don't have many specialists in Chile, we leave the invitation open so that the OAE can help us in this process. In addition, we are in the process of collecting data based on the implementation of a physics guide that uses Kepler third law for exoplanet. In this way, we hope that next year we'll have enough information to launch this instrument so that any educator in the world can apply it in their classroom. So that's all. Thank you for your attention.
Welcome everyone, my name is Ilan. I'm a PhD student at the Leiden University and the University of Applied Sciences in Amsterdam. I'm currently studying how interactive diagrams in astronomy education can help concept learning during practical assignments. I'm doing my research with Joanna Holt, Bert Vedeweg and Pedro Russo. So this research is part of the MindZone project. In this project, a digital tool is being developed that supports hands-on MindZone learning. And this digital tool supports learners in understanding and explaining science phenomena, and it can help teachers to guide these processes. So students perform their own investigations, or they design their own product during these lessons, and then they can make the link with the underlying science concepts to fully understand what they've been doing. So in the daily practice of primary education, the meaningful implementation of science and technology education is a very serious challenge, especially with regard to the actual learning outcome. Teachers find it very difficult to implement inquiry-based science education, and they often lack the formal training in science and technology education to give these lessons properly. Students, on the other hand, really struggle with the abstract nature of astronomy concepts, and they are taught astronomy with textbooks, which also in many cases does not help. So in our tool, we use knowledge representations in the minds-on part of our lessons to help students link the underlying science concept that they dealt with during the experiment that they did or the product that they designed. And these knowledge representations have been proven to positively impact retention, comprehension, and they are visually very intuitive. They can really help students to highlight, but also really improve their science vocabulary and link their science vocabulary to really explain specific science phenomena. So in this study, we also included feedback and reflection prompts to address specific misconceptions while they occurred. The design of these prompts was focused on the visual display of the celestial bodies or highlighted key information about these celestial bodies themselves. So let's have a look at the design of our knowledge representations. The design process is summarized here in 3 steps, basically. So we use the curriculum, the Dutch curriculum for primary education, to choose a subject about maybe here astronomy. And then we choose a cross-cutting concept that fits this subject best. And then we select a diagram type which executes the cross-cutting concept best. So here are 3 examples. So these are 3 parts of knowledge representations from different types of lessons that we offer in the tool. So the first one is from a lesson about sound waves, and here the knowledge representation teaches students cause and effect. The second one is about what can you find in your toolbox, and students are supposed to classify specific objects here. And the third one is an assembly knowledge representation where students learn about the different parts of the bike and their function. So for this study, we have chosen the subject around 14 celestial bodies within our solar system. And we've chosen 3 characteristics which we think students should classify these 14 celestial bodies. So for example, we've chosen here shape, orbit, and composition, and then the 14 celestial bodies are shown below. And then the students are supposed to classify these celestial bodies based on specific characteristics. So for example, here shape, they're supposed to choose, is my celestial body irregularly shaped or is it round? And then they're classifying them. So this is just the first level. So the lesson materials were designed to give students an object, in this case a card, about all the celestial bodies that they can classify. So they can really study and order them on their own table before starting the exercise in the software itself. So the information is kept really short and the focus is really on a visual, so on an image of the celestial body. So whatever they're seeing on the cards on the table, they can find in the application itself. So we use the same imagery and the same language to keep it cohesive. So the first part of the lesson is entirely focused on assessing students' entry level by asking them to predict, to observe, and name different celestial bodies to guide them when exploring the lesson materials. So for example, here, this is one of these questions. They are presented here with the cards that they have on the table as well. And then they're asked, can you name a different celestial body than the ones presented here? And the follow-up question could be, how would you classify planets like Earth and Mercury? So we're really guiding them while they are exploring the lesson materials to do it more efficiently. So I could show you here a little demo of our lesson. So here the students come in and they have to put in a specific code for our research purposes and their name or anything else. And then they start the lesson and they start out with a bit of background information, and then they start out with the question, like the one I just showed you, and then they answer them. And here they don't receive any feedback yet. But as soon as it gets more content specific and we're really asking them about the lesson materials, then they can get feedback. So for example, here, a student can put in an answer, then they're given the right answer, and then they're asked to reflect on their answer. So they're supposed to grade their answer. Does it look a lot like the answer provided or not at all, or just a little bit? And then they're given an explanation. And this process repeats itself until they get to the diagram itself. So when they finally start the diagram, it looks a bit like this. So the three characteristics are here above, and the celestial bodies are beneath them, and then students choose any type of characteristic they want to start with. So I've chosen shape in this instance. And then I'm going to drag all the different celestial bodies in under the right word. So are they irregularly shaped or are they round? And I keep doing this and doing this until I finally think, oh, I think I am done. But then when I click to continue, I see, oh, I've made a mistake. And what then happens is I can click on my mistake and it provides me with an additional question with the visual of the mistake I've made. And we are comparing the cards here to help students reflect on their own answer, but also providing them with a question that really guides them towards the right answer. So here the second level starts, and I can drag any type of characteristic I want. And I've chosen orbit here, and then you see all the previous answers disappear, and they're supposed to start over and think in 2 levels until they choose the final characteristic, and then they have 3 levels, and then all the previous answers again disappear, and they're supposed to think in 3 levels now until they finished answering everything. So in summary, students come into the lesson, they're guided when they explore the software. They do a hands-on activity. In this case, they're exploring cards and the map. And then they move on to a minds-on activity, so the knowledge representation here, and they can consult feedback and help whenever they deem it necessary. So we use the pre-post test setup to assess their baseline knowledge and the effect of the lesson itself. And we collect all types of data logs from the software to analyze. So we are currently still in the middle of our data analysis, but we have some preliminary takeaways. It seems the characteristics, shape, and composition are by far the most popular choice in the first level. There's also some clustering going on when we look at the dragging behavior in the effect group. It seems that the group is really divided into 2 groups. Students who needed to drag at least 5 celestial bodies more than 3 times, and the group that dragged 2 celestial bodies maybe twice before finishing the exercise. There really was no middle ground. There was also a really big time difference between level 1 and level 2, but a lot less between level 2 and level 3. So if you want to learn more about our application, please visit the website here. The app is free, so feel free to use it in your own classes, or if you just want to test it out, please do so. And if you need any more additional information, please let me know. And if you have any more questions or are interested in the software itself, also please let me know. Thank you so much.
is Salen Buchner, and I am the external evaluator for NASA's Punch Mission Outreach Program. Along with my co-author, Sherilyn Morrow, who is the Outreach Director, we want to tell you about participatory evaluation to assess NASA outreach products for classrooms. The public engagement program embedded within the NASA Punch mission extends outreach to primary and secondary classroom students and educators. Traditional evaluation of educational activities includes what we call front end, or maybe a needs assessment, formative, which is ongoing assessment, and summative components, often to show impact, enacted by an external evaluator who solely collects data for reporting purposes. Evaluation for Punch Outreach addresses these evaluative stages, but with some novel twists worthy of sharing and discussing with the broader community. The Punch mission will study the Sun and the space between the Sun and Earth as one unified system. It will study the Sun's outer layers, called the solar corona, and how they expand to become the solar wind that fills the space between the Sun and the Earth, called the inner heliosphere. Punch will use polarized light to study the science of space weather. It will use 4 cameras, each one as a small Earth orbiting satellite, combined to track solar storms better than ever before. The NASA Punch Mission Public Engagement Program is organized around an ancient and modern sun-watching outreach theme to ensure that the science of heliophysics is more personally and cross-culturally relevant to a broader diversity of learners, both inside and outside the classroom. The theme portrays NASA exploration of the sun as a natural extension of humanity's age-old dedication to observing and learning to live in harmony with the sun's cycles. The educational activities are centered on the personal solar observations of the learner and their interconnections with both ancestral sun watching and NASA sun watching missions, including NASA's Punch mission and the Parker Solar Probe. The Punch mission cultivates intentional collaborations among scientists, Indigenous and Spanish-speaking youth and families, Girl Scouts, and blind and low vision learners on developing educational activities that are aligned with research on how people learn. Mission outreach team members test activities in classrooms and with teachers to gather feedback on how they can be improved. By cultivating an ongoing relationship during activity design and revision, the mission ensures that field testing is not just perfunctory, but is a central part of the relationship with these different communities. By this means, what other projects may refer to as target audiences instead become NASA collaborators. In this way, the mission public engagement effort collaborates with historically marginalized populations to create products that are a benefit for everyone. The NASA Punch public engagement effort is made up of multiple institutions across the southwest of the United States. Having multiple core partners with a spectrum of ongoing educational events provides many more natural opportunities for field testing of products with students and teachers in multiple states, leading to excellent products. This leads to an opportunity to leverage formative evaluation opportunities across multiple institutions who are part of the collaborative. I, as the evaluator, am also an astronomy education professional. I was very interested in collaborating on enacting a non-traditional participatory approach to evaluation. The mission needed a low-cost plan that was effective in ensuring the development of high-quality products that benefited all learners. In this participatory model, I regularly attend team meetings and participate in mission activities, including going out and field testing the educational products myself. My extensive background in networking in space science and astronomy education has offered a capacity to gather data and insights from a wide spectrum of participants, from school children trying out our products to research scientists contributing to the outreach efforts. The participatory approach supports relationship development and ongoing conversations with diverse team members and advisors regarding opportunities to collaborate more broadly in the astronomy community and ways to amplify the impact of the project. Another benefit of having an embedded evaluator is one who works closely with the rest of the public engagement team to ensure that evaluation is conducted by all members of the team for the good of the project. A sole evaluator cannot be in all the places needed to collect data for such a large project, both because of time and because of monetary reasons. I help support and train all members of the public engagement team to collect needed data when they are visiting schools or conducting teacher workshops. I also help them critically reflect on the data that is collected. The project leadership helps to cultivate an evaluative mindset among all team members, asking them to provide what we call after-action reports so that they can reflect on lessons learned and ideas for improvement while they are field testing the prototype activities. The results and insights can also be shared across the team and immediately implemented in this way. We are moving beyond just front-end evaluation of needs to ongoing conversations about opportunities with our collaborators. Traditional needs assessments as part of front-end evaluation is a valuable way to strengthen proposals for funding. Punch Outreach is moving beyond this traditional structure to include ongoing conversations and continuous relationship building by team members with collaborators. The participatory framework for evaluation includes attention to teams' ongoing conversations and collaborations with historically marginalized populations so that they are sensitive to new opportunities beyond the results of traditional front-end assessments. With support from me as the evaluator, the team members are attuned to recognize needs and opportunities of collaborators in an ongoing way. So we are moving beyond just a single front-end assessment and really taking advantage of these opportunities as they emerge. Summative evaluation is including, but also beyond, the numbers of individuals reached so that it is intentionally including attention to how the project is benefiting team members, partner institutions, consultants, advisors, and the broader community in an enduring way, so the key insights and lessons learned are shared not only for the project, but for the community at large. As you can see, this project has been able to move on from classrooms to larger dissemination to having scientists share with new individuals who will use them in new classrooms. I want to end by showing two examples of products that we have been using. Seen with your hands is a set of thermoform tactile art representations of the solar corona. These thermoforms were originally designed as an inquiry for blind and low vision learners. Through ongoing pilot testing in classrooms with blind and low vision students in two different communities, they have been adapted for use for an activity called Seen with Your Hands that benefits not only blind and low vision learners, but also sighted learners. The Punch team cards are a set both in a digital and physical format that feature diverse individuals who each support the NASA Punch mission. The team members featured help demonstrate to students the wide range of skills and backgrounds needed to make a NASA mission successful. Each person showcased not only what they do at work, but also what they like to do in their free time. This has broadened the humanity of the team card participants, providing students with inspiring and relatable role models. The team cards have been carefully developed in collaboration with each person featured, and with those field tested the cards in classrooms and Girl Scout troops. The cards and associated activities have undergone several revisions to adapt for a variety of age groups. Alongside the cards are ways for students to engage by making their own team card on a template. We invite you to see the products created through robust formative assessment alongside collaborators in primary and secondary classrooms. All products are free and open to use. We also invite you to reflect on the collaborative way we have conducted evaluation to make the best products possible.
Hola, mi nombre es Fernando Ariel Caraseur. Les voy a presentar el trabajo Asesoría y Pareja Pedagógica para la Enseñanza de la Astronomía en el nivel primario. Pertenezco al programa de intensificación en actividades científicas del Ministerio de Educación de la Ciudad Autónoma de Buenos Aires, República Argentina. Me acompañan en el trabajo María Iglesias, perteneciente al mismo programa, y Alejandro Gangui, quien pertenece al Instituto de Astronomía y Física del Espacio y a la Universidad de Buenos Aires, y además es quien dirige mi tesis de doctorado en Enseñanza de las Ciencias en la Universidad del Centro de la provincia de Buenos Aires. La intensificación en actividades científicas es una de las modalidades de intensificación en un área de conocimiento que propone el Ministerio de Educación de la Ciudad de Buenos Aires para sus escuelas de nivel primario, a las que asisten niños de entre 6 y 12 años. En la actualidad, dentro de las 24 jurisdicciones que posee la ciudad, existen 22 escuelas que están intensificadas en actividades científicas. Esta modalidad posee su propio marco curricular que prescribe las condiciones para que esta intensificación se pueda llevar adelante. Una de estas condiciones es la incorporación a la comunidad escolar de un integrante, que es el asistente técnico pedagógico. El asistente técnico pedagógico reparte mayormente sus funciones en la asesoría y la pareja pedagógica con todos los docentes de la escuela y su equipo directivo. Posee horas para el trabajo conjunto, tanto en el grado frente a los estudiantes, como horas específicas asignadas para la planificación de los proyectos de enseñanza. Si bien el diseño curricular para el nivel primario en la Ciudad Autónoma de Buenos Aires se modificará a partir del año 2025, el diseño curricular vigente hasta este año se ha llevado adelante en los últimos 20 años, presentando los contenidos de ciencias naturales en 4 grandes bloques. Por un lado, el bloque de los seres vivos. Por otro lado, bloque de materiales. Por otro lado, fuerza y movimiento. Y, por último, la Tierra y el universo. El nuevo diseño curricular presenta una reorganización de los contenidos en cada grado, pero en esencia mantiene la presencia de estos bloques de contenidos, aunque con otra denominación y otra organización por grado y a lo largo de la escolaridad. Para este trabajo decidimos implementar un instrumento de evaluación de las actitudes frente a la enseñanza de la astronomía, implementado tanto en docentes de nivel primario en ejercicio como estudiantes en formación inicial. ¿Cuáles fueron los resultados que hemos obtenido? En general, los contenidos asociados con seres vivos y materiales son percibidos de manera más amena frente a los contenidos de astronomía, fuerza y movimiento, para los cuales se asocia fuertemente una mayor dificultad, un mayor nivel de abstracción, aunque reconozcan que especialmente para los contenidos de astronomía son contenidos que mayormente a los niños en particular interpela, atrae, convoca y entusiasma. Son pocos los docentes en ejercicio y en formación que apelan a un enfoque problematizador, especialmente para estos contenidos. Es en este punto donde la tarea de asesoría y pareja pedagógica, entendida como una intervención situada, teniendo en cuenta el contexto específico en el cual desarrollamos nuestra tarea, puede enriquecer las prácticas de enseñanza. Cada escuela intensificada en actividades científicas posee al menos un asistente técnico pedagógico. Los recorridos formativos de quienes nos desempeñamos como asistentes técnicos pedagógicos es diverso. Algunos somos profesores de ciencias, mayormente provienen de la biología, en mi caso provengo de la física, y algunos son maestros de grado con ya varios años de experiencia. Los docentes que han transitado por escuelas intensificadas en actividades científicas mayormente reconocen y valoran cómo se han enriquecido sus prácticas de enseñanza de las ciencias en general, de las ciencias naturales en particular, y para quienes enfatizamos la enseñanza de la astronomía, también de esta ciencia. Es así que han pasado de proponer actividades tradicionales y expositivas a aquellas en las que se pondere instancias problematizadoras, la observación del cielo, el análisis a partir de un registro, teniendo en cuenta que durante su formación inicial los maestros de grado poseen 4 asignaturas específicas donde se aborda la enseñanza de las ciencias naturales y solamente una de ellas aborda explícitamente la enseñanza de la astronomía, nos preguntamos si se reconocería como necesario la necesidad de estos dispositivos de acompañamiento, en asesoramiento y en pareja pedagógica si no se hubiese trabajado en una escuela como las intensificadas en actividades científicas. Además, nos preguntamos si es posible pensar en nuevos dispositivos de formación que contemplen elementos como los presentes en estas escuelas intensificadas. Muchas gracias por su atención, los invito a leer el artículo completo y a contactarnos.